So, good evening, everyone. I would be talking a little bit more about interference of light. Most of it in details have been discussed in class. So, it is more of an overview to all of you so that you get a good brush up and at the same time know a little more of what you need to know from this chapter which you have learned today. So, I am Dr. Ranjana Goswami from the Department of Physics, BP Poddar Institute of Management and Technology. Now, we all know that there are basically two schools of thought regarding theory of light. One is the corpuscular theory. Sir Isaac Newton is the propounder of the theory, and the other is the wave theory propounded by Huygens. And we also know that from the corpuscular theory of light, light has been thought to be moving in corpuscles, and this could explain the laws of reflection, refraction well, but the phenomenon of interference diffraction could not be explained using this theory because the rays, though they crisscross, no superposition takes place over here. It is only under wave theory rays move with their wave front in the form of wave train. They superpose at the region of crossover just like any other wave. All of us know that. Now, well, the conditions of sustained interference, which is very important to know the theory of interference, all of us know that even if the waves superpose, it doesn't necessarily mean that we would be getting an interference pattern. Certain important conditions need to be satisfied, and they are the following that have been shown over here and has been discussed in class, that the rays should come from coherent sources, which basically means that the phase difference between any 2 points of the two rays should be constant. The rays should have same frequencies. The rays should have same or nearly same amplitude. They must originate from point source or narrow source for interference by division of wavefront. They must originate from extended source for interference by division of amplitude. And to obtain good contrast, because that's very important to see a sustained interference phenomena, the background should be dark and the intensity of minima should be 0. Well, what is important over here is uh, interference of light, which was propounded by Thomas Young. Now, the Young's double slit experiment, as shown over here, has light coming from a pinhole and then falling on two very close lying pinholes, almost equidistant from the source, and then these two, the lights, the wave fronts, which are interfering. Well, this is the region where interference is taking place. These rays are allowed to fall on a screen where we see alternate dark and bright fringes. So this screen actually is a signature of the interference pattern that we see after the phenomenon takes place. We have already studied, we already know that this interference pattern from Young's double slit experiment comes from division of wavefront. You can see it from this figure also. The path difference, when this condition is satisfied, we get bright fringes. They are constructive, arising from constructive interference. And when this condition is satisfied, we get dark fringes arising from these at these points. And the interesting part of the whole story is that the fringe width is given by lambda d by d, and it is the same for both bright and dark fringes. Now, the other interference pattern that we see is widely applied, and that is, it has wide applications also. It is interference through thin films. Now, when we say thin film, the question that automatically comes is how thin a film is. And we all know by now that to get interference, the thinness of the film, or rather the thickness of the film, should be comparable to the wavelength of the incident light. Now, for interference occurring from reflected components, for constructive interference, the path difference follows this formula, which has been extensively calculated and shown in class. All of you know it. And for destructive interference, this is the corresponding path difference. And if you observe very carefully, you will see that for the interference occurring from reflected components, the condition is for constructive and destructive interference is just the opposite of what we have seen in Young's double slit experiment. And well, it is important by now for us to know that here, here actually interference takes place by deviation of uh, amplitude, and well and interference that we see by division of amplitude, typical interference patterns that we see by division of amplitude are the ones that we see from Newton's ring, and that basically gives interference from the wedge-shaped film. Now, if we make a comparison of interference by division of wavefront and interference by division of amplitude, well, these are the salient features. Where for interference by division of wavefront, it is, well, the typical experiments that we do is Young's double slit experiment, Fresnel biprism, and that by division of amplitude, it is Newton's ring or interference on soap films. Well, this arises from point source or narrow slit source, and here it arises from the extended source of light. The fringes are basically, if we do the calculation of the loci of the fringe path, then we see that they are hyperbola. But as the path difference is small and the eccentricity is large, they appear as straight lines. Here the fringes are circular for wedge-shaped films, which you have already seen in the laboratory for our Newton's ring experiment. And well, the condition for constructive and destructive interference from reflected light is opposite to that of transmitted light, whereas the condition for constructive and destructive interference by division of wavefront is same as that for interference from transmitted light by division of amplitude. Here in Young's by division of wavefront, we obtain fringes of equal thickness. By division of amplitude, we obtain fringes of equal thickness because the maxima and minima will represent loci of points where the thickness of the film is constant. And also, for illumination of a film of uniform thickness, fringes of equal inclination is also observed. We call them Heidinger fringes. And in case of interference by division of wavefront, the fringes observed change as we keep on changing the position of the screen, and therefore they are non-localized fringes, and here we have localized fringes. Well, it's important for you all to know some formulas regarding the some important formulas regarding the interference of light, and I won't tell you all. Well, these path difference as well as fringe width are valid, as all of you know, or rather it's better you find out. For this is for constructive interference, this is for destructive interference, and our observation tells us that the fringe width is same for both bright and dark fringes. And if you try to find out the angular separation between the emeth dark or bright fringe, this is the condition for bright fringe, the angular separation, and this is the condition for the dark fringe. The symbols have their usual meaning. You should know it very well by now, since your first class test is already knocking at the door. And look at the expressions for the division of amplitude. If you have to do problems, then this gives you the condition for bright fringe for a reflected system, this one, and the condition for dark fringe for a reflected system. You see, it's just the opposite of what we see for by division of amplitude. Whereas for a transmitted system, the condition of brightness is this, the condition of brightness is this, and the condition of darkness is the same as that for deviation of amplitude. The radius Rn that I have shown over here is the radius of the nth ring, which is given by this expression for bright fringe and by this expression for dark fringe, where the symbols have their usual meaning. Now, what are the engineering applications of interference? Because ultimately, since you are engineers, it's important that whatever you learn, the course has its own objective, and this is one of the important objective of this lesson that you are receiving, the engineering application. I don't know how many of you know that thin film, the concept of thin film has been largely used for making anti-reflective coating. Now, anti-reflective coating, as the name goes, is actually a very thin coating, thinness again of the order of lambda or lambda even less, where the reflected light is totally cut out. The power of reflection is made as minimum as possible, as small as possible, so that the entire ray gets transmitted. And this happens actually between three phases. Light goes from air to the coating to glass, having the refractive index following this pattern, and this helps in the cancellation of phases. As all of you know, that when light changes medium, there is a cancellation of phase. Okay, so as the phase cancels, and the power of light is reduced, what becomes very effective is the design of optical instruments, and therefore anti-reflective coating is used extensively in the design of optical instruments. Now, for effective cancellation of the coating phases, the thickness of the coating follows the following formula, and usually lambda is chosen in the middle of the visible spectrum, which is nearly the green light. Now, if we study very extensively the phenomenon of anti-reflective coating, what we observe is that, well, we see that the on-axis refraction is for on-axis refraction, maximum destructive interference occur for green light with considerable refraction from other colors. But when the angle of refraction is, say, theta, on-axis means 0 degrees. When the angle of refraction is theta, the path length becomes longer by 1 by cos theta. So destructive interference is more complete for longer wavelength and less complete for wavelengths close to theta. And therefore, well, such applications, such coatings are used in spectacles where we see bluish tinge or green tinge. Now, this application of thin film is also seen in nature in a phenomenon called iridescence. Thin film interference plays important role in producing variety of colors in birds like peacocks, butterflies, also in ants, butterflies, beetles, and in some of the flower variants. The thin and changing surface structure of the skin and feathers reflect the incoming waves from different parts of the surface, either microscopically or nanoscopically, producing amazing colors, which we call iridescence. Now, you can see in the following diagrams the application of thin films and how the color changes, the corresponding bluish violet tinge. And the interesting part of the whole story is that if the spectacles are given this anti-reflective coating, then one sees the eyes better. The eyes are clearer than when the spectacles are not given the coating. Students, I would suggest that you enhance your knowledge more by studying engineering applications of thin films and therefore of interference phenomena, and you can also apply these ideas in your micro project. Best of luck, and thank you. Thanks to all of you.